Welcome again to electrostatic field. Today we'll have some practice problem in Gauss law of electricity, and the problem is about electric field due to sphere of a uniform charge.
To calculate here the electric field due to a sphere of uniform charge density rho v coulomb per meter square centered around origin in the free space and has a radius of r. Of course, we have many information here. Then first we have the sphere center around 0, 0, 0, the origin. It has a radius of r, and in this free space, this means that we need to use epsilon naught. And of course, we have also rho v coulomb per meter square. So to solve this one, since this is a sphere, then if we are going to use Gauss law, then we just use the spherical coordinate. First thing we notice that this symmetric system, so our electric field basically will come all over the sphere in a symmetric manner. We know that this direction is just r hat. Electric field component is only er. It is in the direction of r, and also it is a function of r. So based on this, since we are using Gauss law, so we care more about d. So the relation between d and e is d equal to epsilon naught e. So you replace here, since this is a constant, then we understand also that d is also a function of r and is in the direction of r. And we need to understand that we have two regions. One region is just inside the sphere, and one region is outside the sphere. So what we are going to do is that we do the solution one time for inside the sphere and the solution other time for outside the sphere. Let's draw the sphere here. We have a spherical charge with r, and we are doing the integration here up to r. This is our surface. So we will do two times. One is left hand side of the Gauss law, I mean this side. So first we need to decide our n. We already explained that our n will be just r. This is our n. So use it. So this left hand side, and this we decided in the previous slide, and this is r, which is n, our n here, and this sine theta d theta d phi. So we need to do this integration. So but before we understand this, all are constants, I mean r squared, and this term also are constant, doesn't depend on theta or phi, so we get it outside. So once we do this integration, we have two parts. We integrate from 0 to pi the sine theta d theta, and we integrate from 0 to 2 pi 1 d phi, because this simply equal to 0 to pi d phi, 0 to pi sine theta d theta. This is very simple integration, you can do yourself, but at the end you will get this result. I mean, this integration will equal to 4 pi, which is just a solid angle of the sphere. And just substitute in the equation here, I mean this one, you will get this relationship. And now we move to the right hand side, q enclosed. So q enclosed is simply integration of whatever charge is inside this surface here. So then we need to define our integration. We have from 0 to r, from 0 to pi, and from 0 to 2 pi, and rho v outside, because we're informed that this one is just a uniform charge. Then we need here this one just equal to from 0 to r, r squared dr, dot from 0 to pi, uh, this one is d theta, and finally from 0 to 2 pi d phi. This is also a very simple integration, just don't forget here sine theta. So once you do this one, you will get this result, which is 4 pi r squared over 3, which is just the volume of the sphere, only the sphere, of course, here, this small sphere here. Finally, close equal to 4 pi rho v, because we don't not to forget rho v here over. Then we equate the two sides, the result which we got here and the result which you got here, and simplify. Then we reach that our dr is equal to rho vr over 3. Then we substitute also for ER, which is rho V R 3 over 3 epsilon naught after dividing by epsilon naught because D is equal to epsilon naught E. And finally, we can get our all because it's just a magnitude, so we know that it is in the direction of R. So our final result will be like this. And here we are doing the integration outside the sphere, meaning that our sphere, this is where the charge lies, we are taking a surface which is larger than this sphere. When we do the left hand side of Gauss's law, we will not have anything different, just the same result because we are integrating up to R, and this is what we have done in the previous slide. But when we are doing this one for the Q enclosed, we don't have Q enclosed except up to the surface of the sphere which contains the charge. We need to take care that this is from 0 to R. In other words, you to get this result, you need to integrate this rho v. You have integration 0 to r capital R squared dr, integration from 0 to pi d theta. Of course, we have here sine theta, and integration from 0 to 2 pi of phi. And this each of this one you get 2 pi, this one you get 2, and this one you get r squared over 3, and in total you will get this result here. Now we will just do mathematical manipulation. Of course, this integration here, don't forget rho v. So you got the overall charge, two sides equate each other. So you get this, and mathematical manipulation you can reach d as a function of r, the magnitude value, divide by epsilon naught, you get er. And just this is a magnitude, so we know that we are in the direction of r, so this is the overall field. If you remember, we have Coulomb's law, which states that E equal to Q over 4 by epsilon naught r squared in the direction of r. If you compare these two results, multiply this result here by 4 by numerator and denominator, I mean this one here, ER equal to 4 pi rho v r squared over 3, and then you have 4 pi epsilon naught r squared in the direction of r. Simply this part here is your q, and so what you can conclude that just this is Coulomb's law after replacement of q by this value. So everything go to the same result.